if it's not zero, if you start looking at other parts of it, say along here or here, those magnetic fields would either be running this way or this way if they exist, and delta L is that way. So the magnetic field is perpendicular to that, if you want to go that route. If the approximately zero is not sufficient. So now we're left with this part out here, this C. The magnetic field outside of the solenoid. Well, the magnetic field that is created by these currents is not just localized. I mean, it does extend out. You know, at some point, the magnetic field created by a current is going to blend in with the background magnetic field coming from the Earth, as well as all the electronics around here. But if we extend this magnetic field to more than just this local area, that means, see, this is going clockwise. So from this middle one right here, I've got this magnetic field that's going clockwise. Or if I go out a little bit farther, and so I have this magnetic field coming to the right, and this magnetic from in blue, and the magnetic field in the left going to the left in red. So I got these magnetic fields going against each other. Now, even though the magnetic field in red is going to be stronger than the one in blue, it is not particularly significant. The difference is not particularly significant because in a solenoid, that distance there is really small. So the magnetic field along path C out here is approximately zero. So all we're left with is this. So let's come up with a length here. Let's do something clever and just say it's some length L. My magnetic field is in the same direction as my loop, as my line integral, the direction I'm going in my line integral. And so I'm left with BL is equal to mu naught N times I. And so the magnitude of my magnetic field in the center of a solenoid is mu naught Ni over L. And textbooks typically take it one step further. U naught lowercase ni, where this lowercase n is the coil density, which is just number of coils per unit length. So if I wanted to figure out what is the coil density of this, I don't actually have to count the total number of coils. All I have to do is take a segment of it and count how many coils there are within that particular length to get the coil density. Which is particularly helpful on this one. You might be able to have a decent guess of how many rows of coils there are. But this one is a lot more difficult figuring out the number of rows, how many rows of coils there are, because these are much thinner coils. As a matter of fact, it's a lot harder to count as well. Which is why in the online lab, and when you get to it, you can just pull that picture up if it will help you. Like did a copy of this, scanned it, and then it blew it up so that you can actually count coils, as opposed to doing the 1, 2, 3, 4, and not being sure whether you actually moved to the next coil or not. Perhaps you're more sensitive than I am with your fingertips. So we now have yet one more equation to do. Now on a test or quiz, I have not played the game. Don't know if I thought this or said this earlier. I think it'll be obvious whether you're using this formula or whether you're using that formula. I haven't done it so where that's that gray area between the two where you're not sure of which one you're supposed to use. I think that's it for the magnetic fields that are created. We're about to get into the consequence of magnetic fields. In other words, what is the force that a magnetic field exerts? Any questions before we delve into that? Still chapter 30. The magnetic force. Magnetic force is exerted on a moving charge. So it depends upon the charge, how fast the charge is going, and the strength of the magnetic field, as well as the relative direction of the velocity of the charge and the magnetic field. So to start out with the case of I have a magnetic field coming out of the board. And again, the reason I have it coming out is it's a lot easier than drawing X's. So that's my magnetic field. And I have a proton shooting into the magnetic field from the right. When it enters the magnetic field, let's say that we have this incredible technique and we can encase the magnetic field into that space right there, which is pretty well possible to do right now, technology-wise. When the proton enters into that field, which way will it be forced as soon as it enters?
Out. Into the board.
All right, so I got out and in. Devon, I wasn't sure whether you were answering it or you're still figuring it out.
I was thinking out myself.
You're pointing out?
Mm-hmm.
Enrique? There's up, down, left, right, in, out. So we got six possible answers.
Well, it's gotta be either in or out.
Could it be more than one or no?
No, the force, as soon as it enters. I mean, the direction of the force will change as it moves, as it changes direction, but just as soon as it enters.
I would say out.
All right, so I think that was 3 outs and 1 in. Joe, do you want to defend your solo answer?
Well, there's no other forces acting in the up and down, left and right, besides the proton moving left. So it can't be up or down. It could be left, like it continues to move left, but it would be left and out, because if you use your right hand rule, it goes this way, and it'd have to come out. And I'm thinking since it's going this way, if it continues to move through there, it would come out and left if it continues moving.
So you're saying out?
Yep.
I was thinking you said in. Did everybody say out?
I said in before.
You said in. Okay. Oh, sorry, Colin, do you want to defend your solo answer?
I don't know, I had a feeling that it was positive particles move towards like negative pole or south poles. But that's just an intuition. I don't really have a defense. It's just kind of what came to mind.
Okay. That reasoning that you had right there is one of the reasons why I want to stay away from plus and minus poles when dealing with magnetism.
Yeah.
Because that's a common misconception there. All right, let's go to the equation. If in doubt, look at the math. V cross B. What's the direction of the velocity of the proton? What's the direction of the magnetic field? Okay. V cross B. V cross B.
Going up.
The force is up. When dealing with a cross product, the product is always perpendicular to the two vectors if you're doing a cross less than 0. But V and B are taking up basically that plane right there. The force has to be perpendicular to it. So when it comes in, suddenly going to have feeling this upward force. Sorry. Suddenly feeling this upward force, and so the proton is going to start to move this way. So at this point right here, when it's going in that direction, what is the direction of the force? So it's going in that, velocity is in that direction. I want my fingers to curl in the direction of B. So velocity is that way. I want my fingers to curl in the direction of B. Matter of fact, the force, as mentioned earlier, the force is always going to be perpendicular to the velocity. I feel like we've seen that before. What kind of force is always perpendicular to the velocity?
Centrifugal.
Say it again?
Centrifugal.
That's the one. I missed what you said, Enrique.
No, I was thinking about something else.
Okay. It's a centrifugal force. So if V and B are perpendicular, as they are in this case, then the magnitude of F is just QVB. It's still a perpendicular force, but looking at the simple case of it's being shot in so that its velocity is perpendicular to the magnetic field, we get QVB. And as mentioned earlier, that's the only force acting on it. That's got to be equal to mv squared over r. Or m omega squared r if you prefer. And so if we solve for, so much we can solve for. Let's solve for q over m. So I'm going to bring m over and bring vb over this side. So I'm left with q over m is equal to, well, that v cancels out with one of those. And I'm left with v over br. Recognize the power of this. This is incredibly key. I have a particle that I don't know what it is. I have a particle and I shoot it into a magnetic field. I have sensors along the way so I know where it is at some particular time. I see that it's here, I see that it's here, I see that it's here. Those form an arc. From that, if I know, actually if I know 3 of them, I think I define the circle. But from those points, I can figure out the radius of curvature. Magnetic field, I can control that. All I need to do is just tweak a little knob that adjusts current, and I can, so the magnetic field typically is something I'll know. The speed, if I know the time and place, I can then calculate what the speed of this particle is. Because if the force is all centripetal, it's only a change in direction, no change in speed. So I can calculate that based upon the experimental data. And now I have an incredibly powerful tool for narrowing down what exactly it is. Because for all the particles I have, charge divided by mass. It's definitely different for proton than it is for the electron. So I could definitely differentiate those two. And all the other particles have varying masses and charges. If I shot an electron in from this side, which way would it be forced? It seems like an abrupt transition, sorry about that, but I will connect back.
Up as well.
Why up?
I think it was, you have motion going that way.
Yep,
The field that way, but because Q is negative, it flips.
absolutely. So the electron would also be forced upwards given the situation. If I had one, so again, I do this calculation, I come out with Q over M, and I'm saying, oh, it's an electron. I have another one with the exact same ratio of Q over M, except for the fact that it goes down this way. What particle is that?
So positron.
Yeah, it's the anti-electron, the E plus. We had a cloud chamber across the way at one point where you actually could see various particles being created, and you put a magnetic field near them and you can start to see them move, curve one way or the other. All right, so we have that. So now, this is a wire. It's not two plates. This is a wire. Let's say current is going down. So Ben Franklin establishes the conventions that we use today. He's still thinking of the electric current as a fluid of positive flow. And so now the question is it really positive charge flow? This is the 1800s, they don't know. We have flow coming down this way. It could be a positive charge going in the direction of just the way Ben Franklin thought, or it could be in a negative charge going the other way. We now have a way of figuring it out. I take my wire and I run a current through it. I connect it to a battery. I know there's the high side and the low side. I know which way current's going to flow because it was established that way. I now put this in a magnetic field. If I am shooting a proton down, or if this is a positive charge flow going that way, which way will the positive charges move once they enter that magnetic field that's coming out of the board? Remember, it will be perpendicular to the velocity and the magnetic field.
It'll go around. I guess they'll try to like.
Not around. Let's see.
It'll spiral. Well, not spiral down.
Trying to think of what you would need in order to get it to go spiraling. You would have to have another. You can create that. You would have to have a magnetic field going one way and an electric field going another way. Then you can get that spiral going.
Okay.
I'm trying to figure out what your hand gesture is.
So it's going down, and then the B.
Right, so it's going down. So you want your hand so that your fingers bend in the direction towards the other one.
Okay.
So V's down, B is that way.
Oh. That makes a lot more sense than.
Yeah. The downside is, you know, our bodies are limited. So
Yeah.
Joints.
So a proton would actually be forced over here. Or whatever, whatever positive, some positive particles would be forced over on that side.
Oh, okay. Yeah, I see it.
Did you see it?
I see when I turn my head, it kind of does matches.
Oh, okay, oh.
Yeah.
Early on, I was doing the same thing where I knew one thing that was right, and so everything else I had to reorient into that position. Looking at it slightly, the same thing, slightly differently. If I establish the coordinate system here, I, J, and then K coming out of the board. V cross B, just looking at directions, V is in negative J direction. B is coming out, so that's in the K direction. So I have negative J cross K. Well, J cross K, we can just, associative property works. Oops. J cross K is I. So ultimately it's in the negative I hat direction.
Oh.
All right, so we have a prediction at least if it's protons, protons will tend to be on that side of the wire. All right, so now, if instead a positive charge flow in the direction that we think of current, suppose it is negative charge flow going this way. So I have a negative charge moving up. Which way would a negative charge be forced?
To the left. I guess the same.
Right.
Is that right as in correct or right is moving to the right?
To the right.
All right, so we got 2 to the right, 1 to the left.
I think to the left.
So we got 2 and 2. All right, and fight. Somebody make your argument.
So if it's doing the same thing I did here,
Right.
curled the fingers, then I went up, curled the fingers to the right.